Okay, let's talk about motion graphs a little bit. Here we have kind of an exciting video. Let's take a peek. Sound is on. Good.
Okay.
So we saw the little stuffed android go up, be held, go down. Let's take a peek
Okay.
again. Don't mind the blue dots. I know they're out of phase.
Okay.
And don't worry about what happens next. It's a wonderful mystery. So, the story we've got, Android goes up, Android hangs out, Android goes down. Now, we might be wondering, is it speeding up, is it slowing down? That's kind of hard to tell from just looking at the video, which is why we dotted it up. And if we dot it up, we see that we get some nice little graphs. So let's switch over and start talking about these. We have here our position versus time graph. This time it's Y because we're going up and down. That's kind of convention. And so we look at this, we might notice a couple of things here. First thing we might notice, this is a little curvy, which is different than what we've seen before. We do kind of get this idea that it goes up and that it comes down. And here we've got a bit where it's just kind of flat and boring. And that's where it's standing still. So now, this is flat and boring. If we drew a line through it, we'd see it's pretty close. Maybe it tilts a little bit, but more or less flat. And so, if we have a flat thing, that means its slope is 0. So that means that the speed is 0, which means it is not moving. But now let's take a look at the sides here. If we look, if I drew a line through these points, it's kind of steep, but up here, it's kind of shallow. So what does that mean? Well, if it's steep, we have a big slope, which means a big velocity. If it's shallow, we have a small slope, which means a small velocity. So, if we're going from big to small, and then stopping, we're slowing down. If we look at the other side, we go from flat to kind of shallow to steep. So we're speeding up. It's a lot of information to pull just from, a little position graph. Let's see how the velocity graph matches. So again, the claim that we had was that we are start fast, slow down, not slown, I don't think that's actually a word. Just kinda struggling with the words. Slow down, stop for a bit, and then we go down slow, and then speed up. Well, speed up going down, which is kind of weird. But let's see how this works. So we start fast, and lo and behold, right here, we're starting fast. Right? This is a speed of 3 meters per second. Our speed is decreasing and slowing down right to about here, and here, 0 meters per second. We're at rest for pretty much this entire area. Which, if we look, pretty much this entire area. And then here, we're now negative, we're going down, and we're speeding up. So that's exactly the story that we expected. We have, it starts fast, slows down, stops, starts going down, speeds up. Starts fast, slows, stops, starts going down, negative, and speeds up. So that's kind of the information we can get superficially. Now let's take a little bit and try to get some analytical information from this. So we'll get clean copies again. Let's take a look at what this might look at right at the very beginning. So this is maybe 1.5 seconds, 0.4 meters. This is maybe something like 1.6 seconds and something like 0.7 meters. So if we calculate V, we get something that looks like 0.7 minus 0.3 divided by 1.6 minus 1.5, 0.4 divided by 0.1, just like something like 4 meters per second, which is maybe a little faster than we expected, but it's kind of in the right area. If we were to check over here, we would see that it's probably slower. But since I didn't seem to pick any good points, and it's kind of tricky to... Well, I guess these might work. I leave it as an exercise to the viewer to figure out what is V here. But that's kind of how this has to work, and we want to just pick a little area and find a line that we think is kind of straight. You can tell it's not a perfectly straight line, so this is not exactly the velocity, but if we zoom in more and more, we can kind of make it a little straighter each time and figure it out. Now what information can we get from over here? Let's take a look. Let's ask how far up it is thrown. So that's basically what is this distance. So remember, this area is equal to the change in position, which in this case is y because it's going up and down. And again, if we look at this, you know, it's not a perfect triangle. We zoom in, like, what the heck is going on with this area? Not actually in there. But we zoom out a little bit, maybe squint, perhaps cover one of your eyes. You know, it's close. So the height of this triangle is 3 meters per second. The base, let's see, this is, let's say, about 1.9 seconds, 1.5, so base is 0.4 seconds, which is 1.9 minus 1.5. And so the area of the triangle is 1/2 base times height, is 1/2 3 times 0.4, is making me really wish I had a calculator here. 0.3, that's 0.12, half of that is 0.06 meters. And let's see how that compares up here. It starts at about 0.4, ends at about 1, a distance of about 0.06 meters. So we can see all of these graphs are going to be related. We can move from one to the other, unless, you know, if I had picked a better line here, that might have worked out nicely for us. But this is the kind of trick that we have to play. And then if we look at this and picked a new triangle, we would probably find a similar story, though again wonder what the heck is going on there. Anyway, hopefully this helps a little bit in terms of, you know, telling the stories that are going on here, identifying what they look like on a graph, and then trying to make some mathematical sense out of it. We'll put up another video later on with some more examples, but right now I kind of gotta get some sleep. See you tomorrow, everyone.